really the point of this. Big data is a big topic, no pun intended, right? I just want to give you some things because there's a lot of external influences with big data, a lot of drivers coming from places outside of your group, application developers from the business, and understanding the lingo and kind of the basic architecture behind all of this stuff is useful in deriving where things should go, right? You can get into the conversation. I want to leave you with some bits that you can use to take back and use rapidly, for sure. Definitions, and slides, of course, on the screens, and we'll talk through them as we go. Really the big bit on big data, and if you look at the Gartner definition of it, the 3 V's as you get out of this: velocity, variety, and volume. These are all components of scale that are fairly challenging to handle with traditional means. My version of big data, my definition is really data processing at a scale that can't realistically be handled by enterprise technology components. This may be a storage platform. It might be a traditional relational database. Maybe you've been hanging on, duct tape and belt and suspenders approach to keeping a database running, a traditional one, solving big problems. We've come across this many times with customers. And there are some alternative ways to solve the problem, but there are some important trade-offs that you need to understand before jumping in. So that's where we'll base the conversation. It's in the enterprise, kind of a poll of hands other than some of the folks that I already know are wrestling with this. How many of you feel like big data is encroaching upon what you're doing on a regular basis today? Just a show of hands. About half the room, which is understandable. And if you're not, or if you're not directly in the face of it, many times your marketing groups, the PhDs in stats, those kind of folks that are trying to solve bigger problems are also doing this, just unbeknownst to you sometimes, the dreaded shadow IT term as that would go. So finding a place in the middle to meet up is important, but new use cases are driving this. Several examples shown here. It's not just about the business generating data, it's about machine data and all the sensors you might have in a device like this. Aggregated Twitter feeds, social media, millions of people contributing content. These are problems that are very difficult to solve with centralized deployments, be they storage, database, or otherwise. And the drivers for moving away from traditional infrastructure, first of all, is scale. A traditional database where you have a single instance running on a server, you're really constrained by the scalability of the storage system in that server itself. Even Oracle RAC, right? There's only so wide that we can go based on some traits of how Oracle works in that type of a configuration. In file systems too, I love this term. If you look at file and directory structures as a means of deriving business knowledge, SAS is an example, as an analysis tool that does this. I kind of call that a way to create data landfills, right? You're going to use what that department needs at any given time. Usage falls off and you end up with potentially petabytes of stuff that is just sitting there not adding value to your business. So kind of uncracking that and finding a way to make it work is very important. Now the other bit here is cost. Enterprise software licensing. Oracle is expensive. Any enterprise software, TIBCO, pick your favorite platform. These are very expensive components that at scale can completely throw a business case out of whack. So you see a lot of the open source world in the world of big data, right? Where the perception of free, and again, there's a happy line in the middle. Red Hat kind of invented a business on this, right? Take the open source and make it friendly for an enterprise. That's a very common bet. But costs are important, and then infrastructure costs as well. And I list long tenured platforms there. Teradata. I worked for Teradata in the mid-90s. It's a very good product at what it does. It's very expensive too. So when you lay out the kind of investment that you need, and it's really just commodity hardware underneath all that too, folks are looking for a way for ways to kind of do that more cost effectively. Ab initio, evaluated them in the 90s. They do what they do, but they are insanely expensive, and they charge for the simplicity that they bring. So these are important drivers, cost versus scale, that will lead, if not our infrastructure folks or application folks, certainly the business, to look at other ways at solving problems. There's a myriad of options. We have quite a landscape out there of products. In this, I could have filled this to the gills with logos of products and different twists on things. Here's some common ones that we have out there. Some traditional companies, Teradata's on there. You look at what perhaps EMC Isilon does. That's very much a node-based scale-out platform. NoSQL databases, Mongo, Cassandra, we'll talk a little bit about them today, and a lot of the Hadoop distributions and what we've narrowed down to over time. So again, if you look at, we had a lot of variety and things are starting to narrow down to just a couple of platforms too. So some maturity certainly moving along as we go. I had a little bit of a flush in my perspective, I'll put it this way. I went to Cassandra Day 2015, told the story a couple of times for sure, but there were 300 people there, really from completely different backgrounds, from the business, from the application and the database side, that were looking at Cassandra for various reasons. A major bank was there. They sent 20 developers for a full day because they're spending money on Teradata and Ab initio. It's killing them. They want to know if a product, a NoSQL product platform like Cassandra, can help curb that investment in any way. So if you're not seeing it, if you're in an infrastructure role, boy, your application teams, your business units, they are out there in droves. I was sitting somewhere in the back on this, but nonetheless, I was very impressed by the breadth and diversity of folks that were there. It was an impressive event to see. Now let's get a little bit into what big data is. Parallel processing, taking a very big problem and breaking it down into digestible chunks. This has been the same for 30 years or however long since, for me, it goes back to the 90s with Teradata and IBM SP2s and highly parallel platforms like that. But essentially, we're trying to break a big problem down into a small one. And here's some aspects that you need to consider when you're doing that. That coordinator function you see at the top, if I have something that's broken into 1,000 pieces to get the job done in a reasonable amount of time, if I'm a developer, I don't want to think about 1,000 pieces. That's just not going to make sense. I need something to make that one logical thing up to the applications that are calling and requesting resources. So that function, it can be a bottleneck, interestingly enough. It has to be well thought out to make things work. And then we're laying data out. I like to use an example. If I have, let's say, inventory data, product data, and I use SKU to distribute data across nodes. SKU is a nice or highly random number that I can spread data evenly across nodes. But then I want to do a report by product category. Well, wait a minute, what do I do? So you have to think a lot about how data is distributed on a system, because redistributing on the fly is sometimes a very expensive operation. So there's some quirks about this that make things, you have to think about how you're going to access the data. That's a very important bit. Relational databases are very different. We'll lay into that too. Consistency and availability expectations, response times. Is it a long-running task? Is it something that's going to run for hours? Do I need single-digit millisecond access for a very large, something that's more transactional but at high scale? Think about these different dynamics that come in. A Twitter feed, carts on a large-scale web installation, right? Just managing all that through and being able to guarantee response times with huge billions and billions, maybe trillions of rows perhaps as you look at things as they scale. So these are important bits, and data types too. A lot of times, perhaps in healthcare, there are data types that are very explicit to a given machine, right? If you have various imaging bits, PACS, there's a number of systems that are proprietary, and okay, if I can run them in parallel, that'd be great, but what's going to interpret it? I don't have anything that I can go and crack proprietary data, so those are important things to think about to see where advantages can be had in this type of a processing model. But again, it's the same problem as we've always had that in laying out what can work on this and what can't, and there's different products that have had different perspectives based on these constraints. Favor one over that. You can't get everything. Pick a couple of things to knock out, and it works well. So let's compare a little bit into things that perhaps, and then big data solutions and how they kind of make some trade-offs to solve the problem. Okay, traditional database. Any database folks here? Relational, there we go, got a couple hands. So what do you do in a database? You think about the data first, right? We normalize, we eliminate redundancy. We have a separate customer table, and then a separate product table, and then a separate inventory table, or maybe a separate transaction point of sale table. And what do we do to ask questions from any angle? The database tries to make it at least reasonable to ask any question. I do joins, right? I join a table. I pick up the columns I need from each table. Maybe I do aggregations. Maybe you want to roll up sales by product category. Think of the different things you can do when querying a database. All the work goes in up front. And data architects, right? Many know, data architects have a very specific gig and the specific way that they look at solving problems. And this is an example. In mine here, sales, transaction, customer, and product table. Joins and indexes help solve the problem a little bit, but in the end, it's an active standby model. I have in a SQL server is certainly, you're running on one node. If it fails, you move the database over to another node. Oracle RAC, as I mentioned, most of the Oracle folks that I know that deal with this, 2, 4 nodes maybe in RAC, and the overhead of maintaining consistency, that's a very important word in big data, consistency in a cluster, there's a lot of overhead in maintaining that. So the overhead of adding another node defeats the purpose of adding that node in the first place. Very constrained. I mean, the limits have increased, right? You know, what was a lot of data 5, 10 years ago isn't very much nowadays, but it's an important bit, and scale is bound here by the installation that you have. Let's take a look at a NoSQL database. NoSQL is a weird term. Really all it means is that they have other means of getting at the data, I guess, when you get down to it. Cassandra calls it CQL. I don't know. It's a way to get the data outright, but there's a very important bit here. This is a masterless design. You have 2, 4, 50, 100 nodes laying out there, and a very lightweight protocol that allows you, when you're looking for a single piece of data, to very quickly get to the node that has it, or a node that has it. Replication is typically very important in this. We don't just replicate data to have another copy around. We also replicate for performance reasons, a very common trend on the big data front. There are no joins. There are no tables, right? There's a concept of a table. It's a wide column thing, but I'm kind of dumping a lot of stuff in a row and then adding a whole ton of them, right? So what if I want to look at something with a different angle, right? On a database, a relational database, I might do an index. I just create another table here and duplicate the thing. No joins is a very interesting bit when you look at this. There's no transactions to this. And I mentioned consistency before too. Consistency in a traditional database, its job one is when you take in data, I've got it. No matter what fails or breaks in this system at any point in time, I've got the copy, the latest copy of that data, and that's where a lot of overhead comes in. Cassandra, you can tweak that. You can say, I'm keeping 3 copies, but once I get 1 copy journaled, let's throw that back and say we're good. Tell the application that you got it, and then you eventually make all your other copies consistent. There's a lag time versus what a traditional database would do. So if you have an application that is absolutely counting on the database to be ACID compliant, to have consistency at all times, maybe not the best use case for this. And you can also do it to where, hey, if I have 3 copies, 2 in one data center, a third in another, you can make it commit all those before acknowledging back, but that's kind of high overhead, right, when you're looking at a transaction. But what this can do, given the very lightweight method to get to a piece of data on a node, you can do single-digit milliseconds, and it's very write optimized. I can get single-digit milliseconds at tremendous scale, hundreds of nodes, and solve problems that way much more efficiently than a typical relational database would, understanding those trade-offs for sure. Data distribution there too, I kind of did a web cart bit. Those are probably a little hard to see. But we're distributing data by something that's very unique, a primary key, and as long as I do that and manage that consistently, I don't really have a schema. I can make changes. I can add columns. I can do a lot of things that the relational guys would take perhaps weeks to do on a big relational system. Okay, now a document database where Cassandra is very much wide columns, where I've got one giant row with 10, 50, 100 columns represented, and you don't have to follow the same format on every row, by the way, which is fairly interesting in its own right too. This is a document, right? And I used an example here of a customer record for me on somebody's website. There's a customer ID for sure, last name, first name, typical bits here. We have an array underneath that, so you can have phone number for work, phone number for cell. And when I do a document, I'm storing the document. I can change the schema as I go. There's nothing telling me that I have to follow this exact scheme. I might have 5 other phone numbers. I don't have to account for that because, again, from a schema perspective, this is flexible. I'm storing documents as opposed to adhering to a predefined data structure in a table. So very flexible in that route. Again, with Mongo, availability and scalability is the primary focus of Mongo. Consistency I can make, it'll eventually get there. As you're dumping tons of data in this thing, will eventually be consistent where all failures would lead to the same result, right? So these are things you have to plan out in your application design when you get going with this. But you can tune this. But again, near limitless scale, sharding is a concept. I always hate that word. It comes out kind of strange. But nonetheless, your shards, we're laying things out. I can have 2 of them, I can have 4, I can have 50. Again, that's the unit of measure, and I distribute data evenly across all of those to achieve scale. Now, moving away from structured data, moving into database, from databases more into unstructured or files. How many folks deal with NAS on a regular basis? I was expecting some more hands here. Now, NAS is interesting, and if you look at the left, I have a file system, and the state of that file system is maintained on one and only one controller typically. Isilon's an interesting example that doesn't do it this way, but let's talk about traditional, perhaps NetApp FAS, VNX on the EMC front, traditional file system-based products. It only fails over if the primary node fails. While it's been very optimized for file workloads, again, it's a scale limitation. I'm really bound by a single, even like if you look at NetApp cluster mode, I'm bound by the performance for a volume on a single controller. This is something you can very quickly exceed and overrun. Consistency, again, is the top priority. If I tell the app that I have the data, if I do an I/O, okay, I've got to have it. No matter what breaks in the system, I'm going to be consistent no matter what fails as it works down the line. Consistency is your top priority. And again, centralized deployment, and this is where my landfill concept comes in. I think enterprise NAS as a means of general purpose file storage is on its way out. It's just a great way. You'd be surprised what you leave behind on file shares, right? Because there's file and directory isn't enough to really derive intelligence about something. Objects and metadata are a much more modern way to solve the problem and a much more scalable way to solve the problem. So transitioning this a bit to the Hadoop front. Now you have what a file system is, which is kind of the control information. And again, I just throw the logical bits here of a path and a file, the name directory, file name hierarchy. That's something that's managed by the controller here. And then you have the data path. The control path tells you what's what as you're traversing the directory tree. The data path, of course, is actually getting the blocks that make up a file that you need to get a hold of. If you look at HDFS, it really breaks those two functions up. So the logical presentation is owned by the name node. Your application contacts the name node. When you find a file that you actually need, I mentioned that controller function in parallel processing before and how important that is and what a bottleneck it can be if it's not designed well. In this case, we just let the application go after it goes after the data nodes. Here's where all your files exist, or all the chunks of data exist that you need to get access to. Send that off to the application. He talks to the data nodes directly. So this ends up being very scalable. That wouldn't have been possible without divorcing kind of the control path from the data path and the actual movement of the data out to the applications. Availability is the top priority. When you write into HDFS, you've got to batch up enough data to make it worth even writing into HDFS and breaking up across the system. If you have a failure in that moment, you have to be prepared to lose that, right? Your application has to think a little bit before there's a period of time that I have to account for data availability. I need to just deal with that because it's a part of how HDFS works. But once you do that, and given those constraints, you can have hundreds of data nodes, thousands of data nodes, and be able to get fairly consistent performance for a ton of different applications. Obviously, to me, this is for big file stuff. Big file data works out fairly well. And essentially breaking those two up, you get near limitless scale to be able to solve problems with. And that's without even getting into what Hadoop represents and the processing that you're going to do up the stream. This is more about just the means of storing things scalably. Co-location, data sitting next to the processes sitting next to the data they need to get access to. These are all common things or themes around the big data platforms we have. Okay, so with those examples in play, again, a lot of stuff to get to here. Quantify use cases and access patterns. What problem am I trying to solve? Do I have an enormous database where I'm accepting a lot of data written in at a high clip that totally defeats what a database in perhaps RAID 5 protected storage could be able to handle with any reasonable expectation? Is it single-digit milliseconds, or is it something that's long-running? Is it an analytics job that's going to run for a couple hours? Those are very different considerations and lead us down hey, Hadoop can be used for a lot of things. One thing it's not necessarily good at is single-digit millisecond response times, right? So the NoSQL guys kind of jump in there, and you find other tools to fit the problem. Understand what they do to achieve scale. Big data platforms, I just laid it out. You can't have everything. You can't have consistency and high scale and partition tolerance. There's a lot of things. The CAP theorem, if you've looked at this, really consistency, availability, and partition tolerance, those are things to do further research on. There's a basic theorem that's been laid out that says, hey, I can't have all three of these. The big data platforms are going to favor availability over consistency. You'll get consistency eventually, but it's something that you have to understand going in because your applications need to be built to appreciate and understand that too. Enterprise infrastructure is not a four-letter word, by the way. It's not a bad thing. Just in my own lab work for Mongo and Cassandra, I've used SolidFire. SolidFire is an all-flash, node-based iSCSI. iSCSI was a four-letter word for me too at one point in time for all of us that have fiber channel backgrounds. Doggone, it's flexible though. Very straightforward, easy to set up. So I've been doing that kind of an implementation as we go. VMware, obviously, the Serengeti extensions, you can fire up and instantiate many, as far as Hadoop goes, you can lay things out, and speed to market's important, and get comparable performance too. That's another bit where the folks that have the white box nodes with the disk in them, the argument is, hey, they're cheap, and I get the scalability that I want. I'd say on the virtualization side, you may trade off a little bit of top-end performance, but again, it benchmarks very well, and it's something you have a lot of control and flexibility with. And Isilon as well is, again, looking at the all-staters here for sure, laying a way to have data in a file format with NAS, but also be able to speak other protocols like HDFS. That's a very important bit. You can land things, don't have to do triple mirroring, you get the protection efficiency of what Isilon brings, and that's an important bit too. So there's some trade-off. Don't think that enterprise infrastructure is dead for sure. There are moments where you're going to have commodity nodes where that's the best case, but again, you can really find a nice balance in between and deliver some great service levels by doing it. And really, we're here to sort through the options. As you have problems, come to us. Happy to help out, point you in the right direction for various use cases, something that we've always liked to do. And that's it for me today. I really appreciate your time.